All right, so this video is going to be covering some general reactions of aldehydes and ketones. And then we're going to cover a specific reaction called the Wittig reaction, as well as some other stuff, of course. So first, let's take a look at some aldehydes and ketones, right? So basically, we have formaldehyde on the left, we have an aldehyde with an R group, and then we have a ketone. So as we go from left to right, we have an increase in steric hindrance due to those R groups, right? And then, so what that means in terms of reactivity is that as we go from right to left, we have increased reactivity with a nucleophile. And that's just because less steric hindrance means easier access, right? And then also R groups are electron donors, so that carbonyl carbon is less electrophilic as you go from left to right, okay? Or it's more electrophilic as you go from right to left, hence the increased reactivity. So there are two different types of reactions with carbonyls, and the first one would be reactions at the carbonyl. So a nucleophile directly attacks that carbonyl carbon. Let's take a look. And of course the R can be hydrogen or an alkyl group. And we have a nucleophile where we can have a strong negative nucleophile, negatively charged nucleophile with, and then water, or we can have a neutral nucleophile, so a nucleophile with like a hydrogen on it, right? With a little bit of acid to kind of get the party started. So we've seen this type of reaction already. We saw that with Grignard reagents, organolithium, cuprates, and then also sodium borohydride and lithium aluminum hydride, right? So the next reaction is at the alpha carbon, okay? Now this reaction is something we'll go over in more detail at a later time, but just to show you what we mean, we have an aldehyde, or I'm sorry, a ketone with a base. And then that once that base is added to that ketone, it basically removes a proton, and then you can substitute that proton with an electrophile. Okay, so kind of looks like this, where you get resonance stabilization of that conjugate base. So you get the enolate, right? Again, we've seen this kind of. So the like keto-enol tautomerization, there was two methods, and but here you go. After the addition of the electrophile with that enolate, we get our alpha substituted carbonyl. Okay. So again, the one we're focusing on is the first one, where we're reactions at the carbonyl carbon. And I did say we've seen a bunch of these already, but we're going to add a few more. All right, so let's say a nucleophile attacks. We get our alkoxide, and then it gets protonated by water. That's really just the quick and easy way to get to that final product, right? So for the most part, that's really what we're doing in this chapter, but there's a subtle difference between when we're adding those typical Grignard or organolithium or the borohydrides and stuff. So one, for example, would be when we have an acid with a carbonyl with a neutral nucleophile. So the reason why we might want to add that neutral nucleophile with an acid is because, well, since it's a neutral nucleophile, it's not as strong of a nucleophile, right? And so that means we need an acid catalyst to help move things along. And so the role that the acid catalyst plays is after protonation of that carbonyl oxygen, it makes the carbonyl carbon more delta positive, or even straight up positive if you kind of shifted those pi electrons to the oxygen to neutralize that charge on the oxygen. And since it's more delta positive, it is more susceptible to nucleophilic attack. And so we can actually have a weaker nucleophile come in and attack that carbonyl. So we'll go ahead and draw that out real quick. Boom. weaker weaker neutral nucleophile attacks that carbonyl, and then we get our final, or one step away from our final product. We're going to have a positive charge on that nucleophile now, and then we can neutralize it. The conjugate base of the acid comes along and removes that proton. What you end up with is the acid again, as well as the desired final product. So since that acid reformed, that acid can be used to reprotonate another carbonyl oxygen and keep the cycle going. So that's why it's a catalytic amount, and we don't need to add more than just a catalytic amount. So substoichiometric amounts, right? And they're pretty much the same processes, but notice the difference was basically the first reaction we protonated that oxygen after, while this second process we protonated the oxygen before, and then the nucleophile attacked. Okay. So nucleophiles. What's our choice in nucleophiles? Our halogens. Those are terrible for nucleophilic addition to carbonyls, right? What do you guys know about my boy Chuck? He's the best golfer known to mankind. So the reason why these halogens are bad is because once you attack a carbonyl, you form an alkoxide, right? An alkoxide is a strong base, and the chloride, for example, is a very weak base. And remember, that's just basic acid-base chemistry, right? We want to form the weaker base. And so this reaction will not proceed forward. It's strongly to the left. And the same goes for bromide and iodide. And so the reason why this is important to note is because when we did SN2 reactions, those were good nucleophiles under specific conditions, right? But they're terrible now. So it's a little bit different, okay? Sources of nucleophiles that we do like are going to be like hydrides, carbanions, like R minus, cyanide, CN minus, amides, amines, water, alcohol, right? So, of course, the last few were those neutral nucleophiles with the positive charge, or with the hydrogen on there, right? This R minus can take the form of this cool little guy right here, this phosphonium ylide, where we have a triphenylphosphine attached to a carbon that's negatively charged, right? As well as a variety of other ways, right, that we've seen those carbanions. But we really want to focus on these two. So those like that cyanide addition to carbonyl groups, and then we'll talk about that phosphonium ylide shortly after with the Wittig reaction. So a carbonyl or aldehyde can be attacked by sodium cyanide with a little HCl. Okay, so this forms what you might expect, NaCN as the nucleophile in this particular example, and it's just, that's what the final product looks like, right? It's pretty straightforward. The reason why the HCl is in there is just because it's required for protonation, of course. And we'll see what we're talking about right now. Let's take a look at the mechanism. Sodium cyanide with a little HCl. That would be the final product. If all we needed to do was draw the product, we should be able to jump to that very quickly, just because it's pretty consistent across the board when you add a nucleophile, especially a negatively charged nucleophile, to a carbonyl. Okay, so that attacks the carbonyl because that's the electrophilic site. We form this alkoxide, and then we can get protonated from some source, right? So HCl, that H plus from there would protonate that alkoxide. But here's the thing. So HCl in the presence of sodium cyanide will actually protonate it, right? And so what we're going to end up getting is, after protonation of that cyanide, we get HCN, okay? And this HCN could be the source of protonating the alkoxide above, right? So I drew H plus because we're essentially grabbing a proton, but from where, right? And the cool thing about HCN is that it is cyanide gas, which y'all know about cyanide gas. it can kill you, right? So super common in spy movies where they have like a cyanide pill in their cheek and they bite it so that they die before they get taken into custody. So also what you know about glow. Anyway, so the product of this particular nucleophilic addition is called a cyanohydrin. Okay, so CN was the cyano group, and then hydrin is kind of like we have that OH on there, okay? We had the same type of product when we had a halohydrin as well. So if that helps you remember it, but cyanohydrin reactions, there's a couple of them that we want to go over. They're actually really cool. One of them is super helpful in terms of synthesis, and the other is just really interesting because it explains why we can't eat certain foods. So, the cyanohydrin in the presence of a base, deprotonation, form the alkoxide, and then if you have a significant amount of base present, then you can drive that reaction to the right to form the cyanide as well as your carbonyl compound. So we're essentially doing the reverse reaction, right? Okay, so again, that's in the presence of base, right? So, and it depends on the conditions, right, with that base, but we can also do another reaction, which is the one that I'm talking about, is synthetically useful. So if we have a cyanohydrin in the presence of water or base, again, we need that water, right, to really make this go forward with the base, but I'll show you the mechanism with acid and water. Excuse me. So what we end up getting is a carboxylic acid, right? Notice that CN functionality is gone, and we have that carbon turned into a carbonyl carbon of a carboxylic acid. So what this reaction is a hydrolysis reaction because we're splitting water, right? Hydro, water, lysis, splitting, okay? And you can see that the components of water would be drawn in red on the right side. And so let's take a look at the mechanism. Nitrogen, being the more basic site, would get protonated by that acid, right? That H plus that's thrown in there. And so what you end up getting is this intermediate right here with a positive charge on the nitrogen. And this is going, since it's an acid-base reaction, it's going to be in equilibrium, right? It's always going to be the case with acid-base. Now, since that carbon is bound to a nitrogen that's positively charged, it makes it more delta positive and more susceptible to nucleophilic attack. And our nucleophile, in this case, would be the water that's present, okay? So this is analogous to the carbonyl reaction with a neutral nucleophile and an acid, right? So now we have this intermediate right here with the oxonium ion with the positive charge on that oxygen, right? 3 bonds to it. So, of course, anytime you have a charge in a mechanism, you want to neutralize that charge or put it somewhere else where we want it to move forward. So I'm going to do a proton transfer where I remove that oxonium hydrogen and then put it on the nitrogen. That places a positive charge on the nitrogen. This is actually an iminium ion. And again, that carbon is more susceptible to nucleophilic attack by a weak nucleophile, water. And once it does that, we've got our, let me gather things in my brain. So we've got the oxonium ion on the bottom, so we can neutralize that. And then we have an OH and an NH2. So again, a proton transfer will take off the hydrogen from the oxonium, oxygen, and then place it on the nitrogen. And what does that do? It gives it a positive charge, right? And so it's a positively charged thing, so it's ready to leave. And so that's what we do. We push it out by creating a carbon-oxygen double bond, and that's pretty much our carbonyl oxygen, or carbonyl bond, right? We got a positive charge on that oxygen, And we also have that amine that left. Okay, so some base is going to come along, remove that hydrogen from that positively charged oxygen in the carbonyl, and it could be water, it could be this amine, right? So this amine, it would be nice if this just got protonated and form an ammonium, because now this nitrogen is no longer nucleophilic and it's really not going to wreak havoc anywhere else. And that reaction is done. We've completed the cycle. We formed the carboxylic acid via the hydrolysis of a cyanohydrin. And cool stuff, right? Super synthetically useful, in my opinion, because cyanohydrins are good nucleophiles. We can just throw them in there, do all kinds of stuff. We used them for substitution reactions in SN1 and SN2, right? Or SN2. And then now we've got it for this on carbonyl reactions. So, good stuff. Now, I did mention that the first reaction is useful in understanding why we can't eat certain foods. So this right here is a linamarin. I'm not going to have you watch me draw the whole amygdalin on the right, but as you can see, they have cyanohydrin functional groups, right? To the left of those cyanohydrin functional groups, we also have sugar molecules bound to one another. So linamarin has one, amygdalin has two. Now, what are these? Why are these important, right? Millions of peaches, peaches for me. Millions of peaches, peaches for free. Peaches come from a can, they were put there by a man. In a factory downtown. You guys know about the presidents of the United States? Fantastic. Great song. Basically, the amygdalin is in peach pits, plum pits, nectarine, any of those weird looking seeds. It's also in like cherries and apple seeds, right? We can't eat all of those things because you got amygdalin in them, right? Another thing that I think it's linamarin is in is cassava root. So if you don't know, cassava root is the source of boba. Boba, delicious. But if it's not treated properly before you make the delicious balls of goodness, then you could die. So, like if you chewed on the root itself, like that. And the reason why these things are harmless is because if you enzymatically break down the cyanohydrin, you get HCN gas, right? Or HCN in the body, and of course cyanide's toxic. So treating like cassava root before actually like cooking it or whatever releases that cyanide and makes it so it's not harmful when you consume it. Okay, so let's move on to the Wittig reaction. So you've seen this in lab already if you have lab, but basically a Wittig reaction creates a carbon-carbon double bond where we had a carbonyl once. So the carbon-carbon double bond is where the carbon-oxygen double bond was, right? And we know how to do this we know how to functionalize carbonyl groups now with like Grignards, for example. But then after we get that alcohol hitting that with acid, forms the alkene product that we desire, but it also forms the more substituted alkene product on the right, the major product. And so this particular synthesis is not useful to form that desired methylene cyclohexane product on the upper right. Okay, so we need a better method, and that better method is the Wittig reaction. Okay, so when we have a carbonyl, that same cyclohexanone in the presence of a Wittig reagent, also known as a phosphonium ylide, where we have triphenylphosphine bound to a carbon that has a negative charge on it. That's the reason why it's an ylide is because it's got a positive and negative charge right next to each other. And this reagent gives us our desired product as our only product. Celebrate good times, come on, do 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 do. It's a celebration. Okay, so that's first of all my jam. You don't even know, but that's super useful, right? Because if we're gonna not form it in a different area, then we are being more efficient with our chemicals, and it's saving time and money, and that's what we want in everything, right? Time is money. And if you're saving time and money, you're saving money squared. I don't even know what that means right now, but anyway, that's so basically one of the other byproducts that I don't really care about that much, but you should know about is phosphine oxide, right? Triphenylphosphine oxide is toxic, and so of course in a lab we would want to know that, and you were told about that if you did the lab. So how do we form that phosphonium ylide, that Wittig reagent, right? We need to work our way backwards. And so remember that phosphorus is actually just below nitrogen in the periodic table. So it does things that nitrogen does, but it's a little bit fancier because it's got d orbitals, so it can have an expanded octet. So I'm just drawing the retrosynthesis of that phosphonium ylide that we use to make the methylene cyclohexane. And this is what we get. We ended up with chloromethane and triphenylphosphine. So triphenylphosphine, again, let me just draw it out for you, even though we should know what a phenyl group is, right? And if you put 3 of them on a phosphorus, it would look like this. And phosphorus, being just below nitrogen, has a lone pair like nitrogen, right? They're the same, meaning it's nucleophilic. So it attacks the methyl group on that chloromethane. It's just an SN2 reaction, right? And that chlorine leaves. So since it's an SN2 reaction, this is the important factor that we want to remember and kind of jam into our brain. Once we have the phosphonium intermediate, we can hit that with base to remove that acidic proton on the carbon, and then that gives us a negative charge on it, and we have a phosphonium ylide. And this can be resonance stabilized, where you form a carbon-phosphorus double bond, but it makes more practical sense to view it like this with the negative charge on there, because that is our nucleophile. And then B is generally going to be a strong base. Butylithium, N-butylithium, N-buly, those are all really much kind of the same thing. The N means normal, so it's like a straight chain butyl group, as opposed to this guy, tert-butylithium, right? These guys are crazy. So, and butylithium, super pyrophoric, right? You can squirt it into the back of a hood and onto like a paper towel, and it'll light it on fire, right? But N-butylithium is crazier. It'll actually just come out of your syringe like a torch. Super dangerous, and unfortunately that was the cause of the death of Sherry Sanji at UCLA, and this was in 2008. Yes, 2008. And totally flipped the industry upside down, because we realized that we weren't being safe enough, and we needed to be more proactive when it came to safety. So really sad. Okay, so we want to make a specific alkene product. So really what we want to do is notice that where that carbon-oxygen double bond was in the ketone or carbonyl group is where that carbon-carbon double bond is. So what we can do is cleave it when we want to make a specific alkene. And when we cleave it, we can place the oxygen on either side of that double bond, right? And then just know that the other side would be, the other reagent reacting with the carbonyl would be the phosphonium ylide. And so what we really need to do is determine which method is better. So what I mean by that is, since we had that SN2 reaction occurring and to make the phosphonium ylide, then we want to do the reaction that has the best conditions for an SN2 reaction. Okay, so for example, this would be the ylide on the left for the ketone, the acetone, and then the aldehyde would have to have this ylide on the right. And notice, if we work our way backwards, the alkyl halide that's needed in order to form those phosphonium ylides, the one on the left would be a primary alkyl halide, of course with that triphenylphosphine, and then the one on the right would be a secondary alkyl halide. And we know that primary alkyl halides are better for SN2 reactions, and so that's the route that we would want to take. This is the best route to make that alkene product, okay, and at least in its highest yield, right? Better conversion to the alkene product. So now let's take a look at how we might actually kind of break that down, right? We have a triphenylphosphine. We're going to attack. I'm going to do this mechanism again because I think we need to see these over and over again in order to really hammer them in. But I'm also, you need to do these on your own, okay? So the reason why I'm doing this one is because I can narrate a little bit more and give you a little bit more info that we need. So once we attack that alkyl halide, we get this phosphonium intermediate. And then again, remember we want to hit that with base in order to remove that acidic proton. And of course, again, that organolithium can just be drawn separately as a salt to really show us where that carbanion is. And then we've got our ylide. Again, remember you can do resonance stabilization with this ylide to create a carbon phosphorus double bonds, and it would be neutral, but I like to keep it with a negative charge because it really shows me where what's attacking what, right? And now instead of having that acetone on the right, I want to put it right where it's going to react. Okay, so I purposely put it here so that way we can do the mechanism for this particular reaction. We have the anion attacking the carbonyl carbon because that's the most electrophilic site. And then the oxygen attacks the phosphorus. They have a strong affinity for one another, phosphorus and oxygen, okay? And so what you end up with is this cool looking intermediate. It's a 4-membered ring, as we know, very unstable, hence it being an intermediate. But this is called an oxaphosphetane, and it immediately breaks down, and we do this cool little ring push around, or electron push around of the sigma bonds, kind of like we saw in the Diels-Alder reaction. And if you follow them, what you can see is that we form triphenylphosphine oxide. So that red bond is from the arrow, and then the purple bond is one that was already there between the phosphorus and oxygen. And then the carbon-carbon double bond forms as well. And so that's the desired product. Take a look there. Yeah. So that's the mechanism for the Wittig reaction. And so that intermediate oxaphosphetane is really important because it actually allows us to form the cis and trans products, even though for this one we don't really have a cis or trans product because it's the same thing, right? There's not different groups on that alkene. But for something like this, we would be able to form a different stereoisomer, okay? Now, this one's actually pretty chill because we don't have to decide which route would be better. We have the same aldehyde and the same alkyl halide no matter which side we put it on, okay? So, again, what we would have is the alkyl halide combining with the triphenylphosphine, and then we get, let's draw this bad boy out, our phosphonium. You've got, there we go, the base comes along and removes that proton to give us a negative charge, getting our phosphonium ylide. Again, this guy is also called the Wittig reagent. And then we can throw that at the aldehyde, right? Methyl ethyl propyl, so it's propaldehyde or propylaldehyde. And then we end up with our desired product, right? And of course, with that oxaphosphetane intermediate and triphenylphosphine as a byproduct as well, but we can also form the cis isomer, remember? So that's the one caveat of Wittig reagent or Wittig reactions is that they form both stereoisomers. Now, you might favor one or the other, depending on sterics or whatever, but in terms of the strength or like the stability of trans over cis, that's not really going to be a thing, okay? And so the reason why we form the cis and trans isomer is because of that approach of that ylide to that aldehyde can be from the top or the bottom. And then we get that's where we get the different orientation in our oxyphosphate intermediate. So we're going to get different stereoisomers as a result. Okay, so let me show you, try and draw this out. So I always have to like think a few times about this when I'm drawing it, because obviously it's a weird structure, right? So let's draw our little 4-membered ring. And what we're going to do is just put wedges and dashes on those guys, on those substituents, if you will, of the ring. And then we'll be able to see where we get our cis and trans from. Okay, so if the phosphonium ylide attacks and we end up getting the hydrogen poking out at us on the top part and the hydrogen pushed away on the bottom part, okay, that would give us one isomer. Let's see, we'll just push the hydrogen, swap it out, put it on the other side. We swap both of them, and let's see. So once we do our little sigmatropic rearrangement, so pushing those sigma bonds around, what we're going to end up with is actually the same products. But this is so we're getting a trans product, but what we ended up doing was since we swapped both of them, we swapped the hydrogen on both of them, we get the kind of like it's looking like the opposite. And so that's okay. Now what we need to do in order to get the cis product is, rather than having the hydrogens opposite of one another, they need to be on the same side of one another. And of course that makes sense because it is cis. So let's draw that oxyphosphate intermediate with the hydrogens on the same side, and therefore putting the alkyl groups on the same side. And same side, cis, right? And so there you have it. So again, this is all dictated by the approach of the ylide. Okay, so it can come from the top of the carbonyl group or the bottom of the carbonyl group, and it really just depends on where it goes. But what we just need to know is that it forms cis and trans isomers, and then it's all good, right? We can kind of explain very simply otherwise. I guess what I mean by that is carbonyl carbons are planar, and then ylide can attack from the top or the bottom, and that's really what's contributing to our cis and trans isomers. Okay, so let's take a look at this one. We have two possibilities for our alkyl group, and we have a benzylic halide and a primary alkyl halide. So remember, benzylic protons are more acidic, and so if we had to remove a proton from there, that means that it would be easier because of resonance stabilization within that ring, and so that's really the position that's going to be easiest. That primary alkyl halide method, of course, would still be a viable option because it would be pretty easy, and it maybe would just come down to cost, like which one's cheaper to do. Can you buy this benzylic halide? The benzylic halide, that actually is a lacrimator, and it burns your eyes, and so maybe you wouldn't want to do that in the lab. Maybe you would want to form the chloroethane instead and use benzaldehyde because it smells delicioso, delicious. Gonna get some bear claws and a Red Bull. Gonna get some. What would you do? You should have some too. I'm gonna promote Red Bear Claws every day now, and Red Bull. So, the Wittig key factors. Since it's an SN2 reaction required to make that Wittig reagent or that phosphonium ylide, use less substituted alkyl halide. Okay, that's again just because SN2 reactions occur faster at a primary position than they do at a secondary position, right? So, and keep in mind, you cannot do an SN2 reaction with a tertiary alkyl halide. So that just wouldn't work anyway, because of, if it's not an alkyl halide, it's a carbonyl, and you can't do a tertiary carbon with a carbonyl, right? So stereoisomers form, right? Cis and trans, and the CC bond forms at the desired spot every time. So that's why it's so cool. And this is unlike the addition of acid to like alcohol. So when you do your dehydration to form your alkene product, that forms the most stable alkene product, while the Wittig reaction just forms it at the position. So the carbon-carbon double bond again forms at the spot that the carbon-oxygen double bond was. And so really easy to spot and work your way backwards from there. So let's do it. Have fun. Let me know if you have any questions.